Our next speaker, I'd like to welcome another one of our colleagues from the Korean Institute of Ocean Science and Technology, Moon-Koo Kim, who's going to be talking to us today about the chemical composition and toxicity potentials for antifouling biocides released during hydroblasting during vessel cleanings. Our last speaker for the day is Mario Tamburri from University of Maryland. This is Mario's second talk in this themed session. Quite a topical one, I think you'd probably all agree, which is looking at in-water cleaning as a source of microplastics in the marine environment.
So thank you all for hanging in there to the bitter end here. I appreciate that I'm standing between you and happy hour, so I'll try to go quickly through this. I first want to say that this topic, I'm not here to sort of sound an alarm, but the more we start looking into in-water cleaning activities, the more complex it gets. And this is just one of those issues that seems to be popping up that deserves further consideration and another deeper look. This specific topic is a sort of a subset of what I mentioned earlier about overall testing of in-water cleaning and capture systems, or in-water cleaning systems in general. So first up, a little bit of background. I think probably everybody in the room is familiar with the issue of ocean plastics, but it's worth a quick review. Plastics can be defined in lots of different ways, and there's some debates about what you call plastic. Fortunately, IMO through MARPOL has defined it in a specific way, which is one or more high molecular weight mass polymers that you're formed in manufacturing either the polymers or fabricating into products. So at least we have a context to think about what we're calling plastics. Now, of course, it's a worldwide issue, plastics in the ocean. You're all familiar with the big garbage gyre, plastic gyre in the Pacific, where this material is accumulating. And it's estimated on the range of 4 to 12 million metric tons of plastics enter the ocean each year. So it's a big deal. The plastics themselves can be toxic, or they can absorb toxic materials. So that's a problem. And these materials can start becoming part of the food web. They're incorporated by organisms and can be incorporated by humans eventually as well. One of the big issues with the plastics, of course, is that they break down really slowly. On the order of hundreds of thousands of years. And so that's one of the major reasons why it's accumulating. It's becoming a huge problem. And so because of that, there's been some actions to try to address this. Of course, through MARPOL, there's a prohibition on dumping plastics by ships in the ocean. I know the IMO and several administrations, several organizations around the world are trying to tackle this problem. And even our conference is plastic free, which is great. When it comes to the issue of microplastics, it's a little bit different in that it's a specific subset of the plastic pollution problem. There's no hard definition of what a microplastic is, but in general, most researchers are now claiming particle size less than 5 millimeters. And this image here is from a recent publication of some of the plastic particles you might see in the ocean. Their biggest concern, with these microplastics is that they have greater biological availability. They're quickly colonized by microbial films, and they can be easily eaten by smaller plankton. And of course, that plankton is eaten by fish, and it moves up the food chain that way. When you think about microplastics, there are sort of a couple of different pathways that can end up in the ocean. The secondary pathway is the breakdown of large plastics, either mechanically, physically, or biologically. So a plastic water bottle gets broken down into small pieces through time. The primary way, though, that these microplastics are getting into the ocean is through the pre-manufactured micropellets and microbeads that are used in personal care products and in fibers. In those two cases, they're sort of a terrestrial source. We're using them on land. They end up in the sewer system, or they wash down rivers and end up in the ocean. But the third sort of one here I have underlined is in marine coatings. Because oftentimes these plastics are used as binding agents for marine coatings. So when you think about the interaction of in-water cleaning and microplastics, you can sort of think about it in this sense. As I mentioned earlier, and we've heard lots over the past couple of days, the The current approach to fouling on ships is through whole husbandry that includes anti-fouling coatings, and these are either biocidal or non-stick fouling release type coatings, and in-water cleaning in one way or another. But these coatings that are being cleaned are made up of about 40% plastics as those binding agents, and there's a few examples of the types of plastics that are often used in these coatings. And it's estimated that about 450 metric tons of microplastics are used worldwide in coatings. So it's quite a large amount. Again, these polymer backbones are binding agents, and they act in different ways on the different types of coatings. There's a real science to how they're used, and the different coating manufacturers have their own recipes and their own technologies for this. This started to become an issue of interest, in particular with a couple of reports that come out over the past couple of years. Back in 2017, the IUCN came out with a report that looked at, and it's the cover there of the report if you're interested, that described microplastics in the ocean in general. And one of the things they concluded is that one of the more important direct releases of microplastics is marine coating, with an estimated 3.7% of the releases of plastics in general into the sea. While that may sound like a small proportion of microplastics entering the ocean, it can be still quite a big amount of plastics, obviously. So because of that report, I believe, but in general, the IMO started thinking about this as well, and they commissioned a report that came out earlier this year to see if there was any information about this interaction, particularly with in-water cleaning. And that's the second report shown there in the dark blue. And there was a lot of, they summarized a lot of primary research as well, and there's an estimate that about 6 to 7% of marine coatings will be lost into the oceans through the life of a ship, but there's no real understanding of how that changes with in-water cleaning. That's sort of the natural sloughing off of coatings through time, and not when you're starting to hit it with hydrojets or brushes and so on. And they emphasize that we need to know more. This next bullet just sort of talks about the different in-water cleaning approaches, and we've heard a lot about that this afternoon, so I don't need to go into details, but brushes and water jets and so on can be releasing these plastics into the sea at a higher rate. So while it may sound like a relatively small proportion, and while the plastics are naturally coming off ships as they move through the waters in their life, doing in-water cleaning in concentrated areas, in concentrated ways, might actually have an impact with the release of plastics that we're not anticipating. So it needs to be something we want to look at. So what we've done is, and we're doing now, is incorporating this issue of microplastics into our tests. And we haven't had a chance to actually implement it yet. I was hoping to show you some data today, but I'm going to show you the methods. And it's actually, I'm glad in some ways it's this way, because we're looking for input and for advice on how we might all proceed down this path. So we've seen this before. How well do these systems clean, and what are cleaning systems? How safe are they from a biosecurity perspective? And are they reducing the risk of water quality? And so the plastics fits right in there. And in fact, even the prior talk, you can replace copper and zinc with plastics and do some of those similar exercises. So what we propose for the sampling for plastics is very similar to what I showed you earlier today when we're sampling for the other biocidal compounds like copper, zinc, or whatever the biocide might be. Same way we're sampling for TSS and particle size distributions and so on. We're simply adding plastics to it with some little changes. So sampling the environment before and after. If I slip to the next slide. So first, continuous sampling of different streams during a cleaning event, whether it's the influent to a shore-based treatment, the effluent from that treatment, around the cleaning unit itself and different distances and so on is going to be important, so we'll keep doing that, but add plastics. Discrete sampling before and after the event, day before, hour before, day after, hour after, to get the background environmental variability as well. But we're going to add some sampling that we don't do for the other components, and that is sampling surface waters, because if they're less, these microplastics are less dense than the seawater, of course, they'll accumulate at the surface. There's standardized methods for dragging plankton nets through and collecting that material. but also sampling sediments underneath where the cleaning activities are taking place. If they're still bound within paint material itself, it may be more dense water sink to the bottom. So there are going to be additional samples required. Volumes might have to go up for our samples a bit, at least 4 liters we're estimating, and maybe a little bit more than that. And sample handling is a little bit different. In particular, we can't use Nalgene bottles. We're going to have to use glass containers for obvious reasons. So I think we have the sampling approach down, but again, I'm happy to hear some input. And then how do we analyze those samples? There has been a lot of work in this area in general because of the issue of ocean plastics, and there's a few papers have come out of the recent couple of years that describe methodologies for how you can quantify and characterize microplastics. The first one by Lance Yankos, he's part of our team. He's sort of an expert in this in the Chesapeake Bay area. This Masura paper is a report that was put out for NOAA on methodologies for how you might quantify and characterize plastics. So there's some simple approaches that are out there now that are sort of becoming standard in this field. One thing you can do, of course, is to filter the water and separate out the solids. Then you can remove the organic material and look for the inorganic things like plastics, and then density separate them, right? So sand grains will sink and the plastics will float to the surface. And then you can analyze that material for their size and their shape using microscopes. And you can characterize their concentrations either by volume or by mass if it's a water sample or a sediment sample. And what's really interesting is that there are now molecular tools that you can use to sort of characterize or fingerprint, if you will, the type of polymer, the type of plastics that are in your sample. And there's a variety of methods sort of listed there that have the capacity of doing that. GC mass spec sort of approaches, or Raman spectrometry, and so on. So there's a toolkit out there that we can adapt for this application. So this slide in particular, I'm hoping to get some advice on from all of you experts as well. This is how we're proposing to move forward in the characterization of microplastics that we might find in our sampling. The first bullet is really, it's not really a method, but it's sort of an approach to how we should do this. It's going to take some coordination with the ships and with the coating companies. We need to know what types of coatings are on the vessel that we're cleaning, and sometimes there's multiple types of coatings. And we need to understand to some extent from the coating companies what sort of signatures we might be seeing for plastics. I know there's secret recipes and there's proprietary information, but if there's opportunities to work together on that, it makes this process a lot easier. We can contribute the plastic signal to either the ship coating or to the environment, because we know there's already plastics there. Then for the sample itself, for the analysis, we're proposing filtering down to 50 microns to remove the solid material. Then we're going to do some digestion of the organics using concentrated peroxide treatment. Density separation, we'll probably end up using hypersaline brine solutions, but there's other approaches for that, separating out of the floating particles. Size and shape, of course, we'll use microscopes and some imaging analysis systems. And then for the molecular composition or fingerprinting part of this, we're going to probably work with Microman or micro-FTIS spectrometry for identifying what kind of polymers they are. So I just want to wrap up by proposing something else we can do. And these ideas came together for our team around plastics, but I think it has broader applications. In the future, these operations are going to become commonplace, and there's going to be some permitting and approvals of those activities. And as part of that process, I would assume, and regulators can chime in, that there's going to be some requirements for periodic assessments of what that operation is doing to the environment. So it's likely that there'll be water sampling like we're doing for the testing that happens quarterly or annually at those locations, and then you show the regulators that there's no increase in biocides or plastics. So I assume that's going to happen in the future. But I also think we want to propose another idea. There's another opportunity to look at the broader impacts of these activities on the ecology and perhaps human health. And that is to take advantage of a tried-true program that's fairly straightforward and fairly simple, but fairly powerful as well, and that's the Muscle Watch program. This is an effort that was started, it's probably 20, 30 years ago now. In California, it's spread since then. It's now around the world. In the U.S., NOAA sort of coordinates the activities. And basically what it's based on is looking at, originally it was mussels and their tissues for accumulation of pollutants, particularly things like metals, copper and zinc. And now in the recent past couple of years, starting to look at plastics as well. So you can use native organisms that happen to be growing nearby, or you can put out cages of oysters or whatever other native bivalves you like, and check and monitor their tissues for accumulation of materials of concern, including plastics. So what we're proposing is that in the future, as these operations start building up, perhaps mussel cages next to the in-water cleaning activities and others in the port, but a distance from those activities, to see if there's accumulation of these compounds and these plastics into tissues and then ultimately into humans perhaps as well. And so I'll just end here and summarize with this last slide, and that is, ocean plastics pollution is a big deal globally, and something we all need to sort of think about in the context of everything we're doing. And again, while the release of microplastics from marine coatings might be a relatively small percentage of that overall pollution, is probably something we want to still keep in mind. While in-water cleaning it's one of these rare examples where you might have benefits both for the industry through their operational parameters and saving fuel, and the environment through biosecurity, risk reduction, and biofouling. We can't lose track that activity itself might have an impact, and we want to make sure we measure that if there is one there. So rigorous, again, standardized and independent testing of in-water cleaning is important, and we want to include things like microplastics now as well. And I'll just end with that same slide I showed earlier with the rest of the team, and I went quickly through that so you guys can get to happy hour. So thank you for your time.